Welcome! In this tutorial we are going to prepare toolpaths for a smooth model in XPS with buildings included. So let us upload the exported file and upload. It might take quite a while, but now it has been properly uploaded. We can double click to open it. While still in the design workspace, we can right mouse and click this previously exported and uploaded polyline document with lines to be engraved for property line and roads. So we'll insert this in the current design. And we click OK. Now we change to manufacture workspace. We'll create a new setup. And the first thing we should make sure is that the origin point is correctly placed. At the top corner, where the two axes are tangential to the edges of the stock material in the positive axis direction. So where x-axis and y-axis, where they both point along the edge and not where one points outward of it. So this corner here. In the second tab, we'll make sure that stock side offset is set to 0 mm. Make sure not to change the default units in all the fields, taking care only to replace the digits that you want to replace. So let's change this to 0. Top offset can be set to 1 mm, it is sufficient. The bottom offset in this case must be set so that the total height is approximately within 0.1 mm or so, 100 mm. So we need to add, what do we need to add? 22.33. 22.33, 23 or so. When you have a material sheet such as 100 mm XPS, it is advisable not to increase the top margin excessively, instead having excess margin on the bottom, because anything that you add on top will increase the time it takes to mill and contribute to waste of material. These stock dimensions are to be taken note of, because these are the ones you prepare your physical stock to. Click OK to confirm. This warning dialog will prompt you to ignore or not ignore the fact that no models were selected and all input models will be used as models, which is correct. Yes. The first thing we can do is save. Ctrl S or click the floppy disk icon there. The version description can be left at default. It does not influence the name of the file, only the description of the different versions. Go to your preferred web browser and go to cnc.kthcnc.se. It's only a URL to a Google Drive. And here you can enter the reference photos subdirectory. And in here you can botanize between the models that students previously have milled. And all of these reference images have indices adhere to them so that you can easily, in the Fusion 360 subfolder, the CAM software that we use, and the community feeds and speeds datasheet, you can easily find the toolpath settings that were used for a specific reference that you find of referential value to you. In this case, we have prepared these sets of 4 toolpaths that are of great referential value for this specific set of tutorial toolpaths. So we will be using these settings for these 4 toolpaths as our initial values. We'll see if we need to tweak them. So as for the first toolpath, we use the Routerbit product ID 23, and it's a 3D adaptive toolpath. So we can go back to Fusion 360 and we can add a 3D adaptive clearing toolpath. We can select a tool, and having previously imported these two libraries, we can go down to, in the Multicam 3000 series one, number 23. Very good, this is the one. Take note here, it is fairly short, so it only has 68 mm from the tip of the tool to the bottom of the collet or tool holder. So we'll need to make sure that this tool does not extend further deep than 67 mm or so. We can select this, and then we can see the datasheet. We can go back here to the spindle speed, the rotational speed of the spindle. And we have 5000 RPM, which is the default value. That's very good. Make sure to only change, if necessary, the spindle speed, and never ever change the ramp spindle speed from the default value. The ramp spindle speed value will be erroneously interpreted by the CNC machine, and it will run amok, ramping its feed rate instead of its spindle speed. In this case, 5000 RPM as default spindle speed is good. The cutting feed rate we can change from 1000 to 4000. It is good procedure to only change the digits that you actually need to change instead of deleting everything here or replacing it, since a unit here should be properly retained. As per the reference, if you hold shift and scroll here, we can see here that we have pull away, and we will enable shaft and holder and have pull away as the active mode, and then change the shaft clearance to 2 mm. thus increasing the safety margin between the non-flute shaft segments and unmilled material. We can go to the second tab, and here we don't need to change anything. We can have no machining boundary as per the reference, and we'll have rest machining active, which means that this toolpath and succeeding toolpath, that they will work in collaboration, and the succeeding will take into account what the previous has milled away so as not to mill the same volume twice. And we see that we have rest machining here. We can go to heights, and here's important that you remember that the tool distance from tip of the tool to the collet was merely 68 millimeters. So we'll need to make sure that the bottom height from the stock top is offset by no more than -67. That's 1 millimeter clearance. It's adequate. Then we'll go to the fourth tab, and then we'll make sure, since this is XPS and a type of plastic, extruded polystyrene, that we don't want to go conventional, because that would increase the risk of rubbing against the plastic, thus increasing the risk of it melting. So we'll do climb as direction, and the maximum roughing step down can be set to 20 millimeters. The fine step down here can be set to 10 millimeters. That means that we leave 10 millimeter vertical increments for the succeeding toolpath, which is okay. We disable flat area detection. It adds very much to the computation time of the generation of the toolpath and does not serve us any purpose. As for the stock to leave, we'll make sure that we leave 4 millimeters of radial stock to leave. This will automatically, by parametrical dependency, change the axis stock to leave to 4 millimeters as well. When milling with a ball end mill in XPS, the surface gets very rough. And it is not a problem, because we are going to define the final surface with the succeeding toolpath, but we want to make sure that we have a sufficient margin left to the actual model, so that any potential areas which gets ripped away significantly does not infringe on the actual surface. In the fifth tab, linking, we do not need to change any settings. Those settings that we needed to change are here in the comment, so it can be good to take this reference and simply follow it. Generally, the later the reference, the more reliable it is, owing to the amassing of collective knowledge. Alright, we can click OK to generate. Alright, this toolpath is simulated to take 1 hour and 15 minutes. The actual time it will take to mill will significantly deviate from that. The statistical maximum to be expected is a time factor of 1.8 for 3D adaptive clearing toolpaths. If we go to Rhino and open Grasshopper, and if we go to gh, as in grasshopper.kthcnc.se, and if we go to definitions, and if we go to fabrication, and if you go to estimate CNC toolpath times, here there is a Grasshopper definition as well as an image preview of it that you can use to perhaps more easily compilate the simulated times and the expected actual times, and we'll do so now. So we'll simply open that, and then for the first toolpath it is 1 hour and 14 minutes. And it's a 3D adaptive clearance toolpath. So it's expected to take 2 hours and 14 minutes. Generally, it's good that the clearance toolpath or the initial toolpath does not take more than half of the maximum allowed toolpath time of 6 hours in total, because this initial toolpath will not define the end result or the final surface, and having an excessive amount of time for the clearing of excessive material and a relatively shorter amount of time for the final surface, it might force the final toolpath to be sufficiently shortened in time. So if this would have been significantly longer, perhaps more than half of 6 hours, so more than 3 hours, then it would be wise to reduce the size of the model so as to more properly define the end result with the final toolpath succeeding. Alright, but here we have it, 2 hours and 14 minutes. This one and first toolpath is expected to take a maximum actual milling time of. And then we want to do the one that actually defines the surface. And if we check the reference here, we see it is a 3D parallel one using tool product ID 19. So we'll go here and 3D parallel, and we'll select another tool, and we'll select from the Multicam 3000 series, we'll select tool number product ID number 19. It's a very long tool with a relatively smaller diameter. It has a length below holder of 125 millimeters, so we don't need to take into account any specific bottom height restraint due to the fact that the length below the collet or the holder is more than the material itself, 100 millimeters. we can click select. The spindle speed as per the reference should be set to 10,000 and the feed rate to 2,500. So 10,000 and the cutting feed rate 2,500. It is good procedure to enable shaft and holder and making sure that it is not trimmed but pull away. In this case, we might see that the difference between the lowest point and the highest point is less than the flute length, but should they not be, we still want to activate this as a safety measure. It makes sure to generate a toolpath where the tool is pulled away from any potential collisions between shaft or holder and unmilled material. We'll go to the second tab, Geometry. Here it's important with a 10mm tool that we have from the tool center on the boundary, which is the silhouette of the model, that we allow an additional offset of a little less than the radius. So 5 is the radius, so 4mm additional offsets. This is to make sure that the tool defines as much of the total area as possible, but still not being allowed to pass past the edge, which we would have allowed it if we would do 5 or 5.5 or more. So we'll do 4 and no more. Rest machining can be kept disabled in this case because we are following up a 3D clearing toolpath with another type of toolpath. The free adaptive clearing toolpath is always calculated from the top, going towards the surface, while the parallel toolpath originates from the actual surface. And then if there would have been excessive material left, then one perhaps would be required to do multiple passes, but that would still be offset from the original surface. So we can leave rest machining disabled here. In the third tab, heights, we don't need to change anything since the range of the tool is more than sufficiently long. And in the fourth tab, passes, we need to make sure that the direction is set properly. And with these circumstances, it's okay to go both ways. Preferably one should go only one way, that is climb milling, so as to reduce the risk of the router bit rubbing against the plastic material when it goes the other way. But generally, and historically with this specific tool and this specific material, it has worked very well to go both ways. And going both ways will save some time, allowing us more time to decrease the step over or adding perpendicular passes. So let us do both ways. As for the step over, we can actually start with a fairly high value, like 3mm, a little more than half of the radius. The good thing about authoring parallel toolpaths is that it's a very linear endeavor. If a step over of 3mm takes 3 hours, then a step over of 1.5mm will take 6 hours, etc. We'll allow it to be 3 at this initial stage, and we have no multiple depths, we have no stock to leave. And as for the multi-axis, we only have 3 axes, so we leave that as it is. For the 6th tab, linking, we leave everything as it is as well. So we'll go back to passes, 3mm step over, we click OK. And while this icon does not tell much, when you hover the mouse cursor above it, you see that we have 13.8% progress. It's not a linear thing. And now we have 18.1, so you can more properly see that it actually progresses. Alright, very good. Now we see already here an approximation of the simulated time. Let's input it into Grasshopper. So we had 1 hour and 33 minutes, 1 hour and 33 minutes. And the type of toolpath is a 3D parallel and we go both ways. So now we see here that the estimated reasonable max time for these two toolpaths is actually only 4 hours and 1 minute. So here we can actually experiment a little. We have 2 additional hours approximately that we can utilize for the second toolpath. And if we see it is only 1 hour and 47 minutes, this one. So I would say that we can utilize this time at disposal to add an additional pass. You will see here, if we simulate this, go to Actions and Simulate, and then we can jump to the end of the toolpath, make sure to disable the visibility of the toolpath, make sure to enable the visibility of stock, change the colorization of the stock from operation to material, and then optionally you can change the material from ceramic to wall paint, which is a little less glossy. You can do however you want. But if we now hide the models, we see that, well, we see a resemblance to the original model, definitely. The vertical cusps are very accentuated. It is of course due to 3mm being a step over that is quite large, a step over of 2mm is more moderate, and a step over of 1mm is very fine. But since we are using XPS, which has no direction of fibers, etc., instead of decreasing the step over, which might be a more viable option with solid wood, in this case I think that the vertical cusps will be better handled by adding a perpendicular pass. By adding a perpendicular pass, it will of course double the toolpath time, which in this case we are within budget to do. It will not change the surface of the model as much as the first pass did, but where the cusps are the most expressive, those are also the areas where a perpendicular pass does most benefits. So let's see, if we exit the simulation, and if we double click on the icon there so as to properly enter the settings here again, if we go to passes, the 4th tab, and add perpendicular passes, and that is the only thing that we do now, and click OK. Alright, we see here that we have an approximation of 3 hours and 6 minutes. So let's go back to Grasshopper, and it was 3 hours and 6 minutes. So we have 3 hours and 6 minutes. And this gives us approximately 5 hours and 48 minutes to expect as a reasonable maximum time it takes to mill. As such, we still have 12 minutes for the 2 succeeding trace toolpaths, but those generally take a very short amount of time. Very good. Let's go back to Fusion, and we should also simulate just to verify how it looks. So let's go to end of toolpath. We will see how it starts by going parallel to the x-axis, and we see the vertical cusps that we previously saw. And we'll see now that it starts to do it along the y-axis if it significantly improves. We saw it improving significantly or not. You'll be the judge. Whether or not the perpendicular pass was worth it in terms of improving the final surface is a question left to you. The main important thing is that the toolpaths that you prepare are safe to run, that is, no critical collisions, and reasonable in time, that is, not an expected time to mill exceeding 6 hours. Let's leave it like this, it looks good. So let's exit simulation, and then we could either simulate and verify collisions now or after the 2 last toolpaths. As long as you do it, you can do it whenever in the process. If you do it early on and you identify a critical collision that you either way would have to readjust the settings or so, then it might have been beneficial. But in this case, we can simply do all 4 of them and then one after each other verify for collisions. If we show the models again, then we can actually do like this. We can open a previously authored CAM document here, and then we can copy the 2 toolpaths that we did for these very lines in that model. So we'll double click here, and then we select this one as well as this one, and we'll right mouse button click and do copy. And then we'll go back to the previous document, and then we can right mouse button click the setup 1 here, and do paste. And here we have them. Having copied these, we can close this, the other document. Now we can open this 3rd toolpath, and we can make sure to delete the curve selection there, because that curve selection resided in the other file. And then we go to the 1st here, and for this specific tracing, this is tracing of the roads. And we'll be using tool number 19, the very same tool that we used previously. It is shown here as a separate instance, but they are the very same. It's just because they resided in different documents initially. And then 10,000 as spindle speed is adequate, 2,500 as cutting feed rate is adequate as well. We also see this if we go to the reference, and if we highlight this one, we have 10,000 and 2,500. That's the feed and speed of our reference here. And we also have a suggested axial offset of -1 millimeter. So we'll see here, if we go to geometry and first of course select the curves, and it was the road curves, these. So let's make sure that we expand this and expand the contents of the reference document, and then expand the sketches, and then we select the roads. Very good. As for the heights, there is nothing we should change. As for the passes in the 4th tab, here we have the axial offset of -1 millimeter. We'll see if this looks good. We can also do less than so, and in linking we don't need to change anything, so we can just go back to passes, verify that everything looks good, and click OK. Let's go to actions and simulate to see how this looks, and then we can hide temporarily all of the models, and then we can go to end of toolpath. Yes, this looks very good. Alright, we can exit simulation, and we can show the models again. And as for the 4th and final toolpath, I think that we should exchange not only the curves, we can delete those as of now, we should change the tool to a V-bit, and a V-bit we only have one of, the 45 degree one with a total of 90 degrees, and we can select this, And then let's see here, as for the spindle speed, let's check the reference. Let's highlight the fourth and final here. We have a reference here of 12,000 RPM. So let's do 12,000 RPM. And then as for cutting feed rate, we can do 2,000. And then if we select the geometry, we should select the property line. Very good. And then as for the heights, we don't need to change anything. But for the passes, here it is 0.5 millimeters descended. With a 90-degree tool, that means that the groove should be 1 millimeter in width. It also depends relating to the actual slope of the route it takes. So let's try negative 0.5 millimeter. Okay. And let's go to actions and simulate and jump to end of toolpath and hide the models. And here you see what I said about the slope, that when there is a significant slope, it will widen. Here, of course, it looks very accentuated because there's a different hue between the unmilled material and the milled material. In the actual result, it might not look this accentuated. The line looks good. Yeah, it's a little wider at some parts, but I would deem this definitely good enough. When simulating individual toolpaths, the other toolpaths are significantly deteriorated. As here, you see that the road engraving with a flat end mill looks very weird. But if we actually do simulate that one and jump to end of toolpath, we see that it looks good. Alright, let's make sure that we input also the time of this. We have 2 minutes. Only 2 minutes, and it's also a 2D operation. That's good. 2D operations have very small time deviations. And the last one was 1 minute, I think it was. Yes, and it is a 2D operation. So we have 5 hours and 51 minutes of expected reasonable max time. That's good. That means that we can go back here and go to actions and simulate, having selected only the first one there. And we have at least one error. We want to show the issues later on. But first we can go to statistics and we see here the time it takes to mill and the machine distance. And now we can go back to info and we have as of now 20 collisions. We can view the issues either by clicking this link, or if this has disappeared, you can go to information and issues. And we see here that we have 20, and all of these are rapid move collisions. Fusion 360 is material agnostic and does not know what type of material we are actually milling. For Fusion 360, this might as well be solid wood, a harder material. In this case, we have a very, very soft material. If it does a rapid move into the stock, it generally is not critical, but we will need to visually verify this, of course. So let's click the first one. And I think that it's sufficient to simply look at it from like this, because if it registers a collision here, then it is the progressing or the preceding movement that is the collision. And it will simply go down, and it thinks that it collides with this there, but it is not a problem at all. That's a non-critical registered collision. And then we can move forward. That's not a problem at all. The third one, not a problem at all. Fourth one, same area, not a problem at all. Fifth one, not a problem. Sixth one, not a problem. Seventh one, not a problem. Eighth one, not a problem. Ninth one, not a problem. 10th one, not a problem. 11th one, not a problem. 12th one, not a problem. 13th one, not a problem. 14th one, not a problem. 15th one, not a problem. 16th one, not a problem. 17th one, not a problem. 18th one, I actually can't see that one. Not a problem. 19th one, not a problem. 20th one, not a problem. Very good. So while Fusion 360 did well in registering 20 rapid moves into stock, as you see here, it is so very little that it collides with unmilled material, and the material itself is so very soft. So in this case, it's not critical at all. We can close the issues here and exit simulation, and then we'll simulate this one, the parallel one, defining the final surface, and we can go to info and wait for detected collisions. We have already seen how it looks, so we don't need to jump to the end of the toolpath to see that once again. If we do, it halts the collision verification, instead focusing on doing the visual stock simulation. So I'll go back to the beginning so as to allow the collision verification to continue. And we have no registered collisions, that's very good. We have 3 hours and 7 minutes and 466.5 meters of machining distance. We can exit simulation. And for the 2 trace operation, it is of utmost importance that you actually verify all of them. In this case, we have such a long tool that there will most probably not be any collision. But we will still have to visually verify that we see that it progresses here along the trace lines. It's not a problem at all where it passes. Not a problem at all. Very good. All right. No collisions registered. 2 minutes. Click Exit Simulation and then visually verify the 4th and final, the 2nd of the trace operations. Let's see here. Let's start a simulation. Oh, that was too fast for me. Let's go back and then decrease the speed a little, the playback speed a little. And here we see that there's no problem. Yeah, and the slope was quite aggressive, so to say. Great, that looked safe. We can exit simulation. We can save the file, Control S or clicking the floppy disk icon. And we don't need to change anything else than the default user saved as a description. That is only the version description for the different revisions of the document. Let's show the models again. To get an accurate preview of the simulated stock, you can select the whole setup, setup 1 here, and then you can simulate. Now you can go to the end of the toolpath and allow some time for Fusion 360 to generate the simulation of the stock. We can hide the models. See here, the trace line is very, very vague, but I think it is okay. What we want to see is that if we right mouse button click the stock and then highlight stock and then save stock, and then we can save it as a default name in the downloads folder here, and then we can go to that downloads folder, and here we have the exported stock, and then we can go to Rhino, and this one we have already verified that is good, so we can save it and close it. And we can double click here and then we can open the file that was our specific CAM file, and then we can actually just click and drag this in here and import it. And default STL import works fine. It should be selected by default when it is successfully imported, and then we can move it 600 millimeters in the positive y-axis, and then we can change the display mode to Arctic, and now we see more properly the engraved line here. Very good. It was more Fusion 360's lack of a proper shading. Alright, this looks good. And one can clearly see the relationship between the original 3D model and the simulated CNC fabricated one. This CNC fabricated model is expected to take 5 hours and 51 minutes to CNC fabricate. And if we select it here and change that there, that can be compared to this one that takes also approximately 6 hours, which has a different language, and you'll be the judge as to which one is the best representation of the site. But it's a very good demonstration that when you mill parallel and allow the CNC to adjust the Z-axis depending on the actual height of the specific point in the way of the surface versus forcing the CNC to stop at certain intervals, one can really see with the sort of same time frame what can be achieved. That this terraced model is a much more time-consuming workflow, and that the parallel one is a much less time-consuming workflow, because the two being given approximately the same time, this achieves a higher degree of fidelity than what there is time to achieve for the terraced one. Nevertheless, one of the two might be what you personally prefer, and as long as the toolpaths are safe to run with no critical collisions and within a reasonable time of a maximum of 6 hours, both are totally fine. Let's go back to Fusion 360. These issues we have already verified. It was in the first toolpath. We can exit simulation, and then we can separately export the toolpaths. While it is possible to export all of the toolpaths in one combined file, since the CNC machine perhaps once every 2 weeks freezes up during operation and the toolpath will need to be restarted or manually split, it is advisable to separately export them as individual toolpaths. So select the first one, go to Actions and Post-Process. As for the post-processor, make sure to choose from Library the one that you have already downloaded and imported. Make sure not to update these post processes, because that would overwrite the custom changes made to the previous version that functions as it should. So we can select that one. The output folder can be changed by clicking the select output folder icon here. Make sure that it is somewhere where you actually can find the file. And then as for the name, it's quite a strict syntax. And it's due to the fact that the CNC controller will not accept file names with special symbols or even spaces or periods. And also that it's only 1.5 dozen or so characters that are showing in the CNC controller. It's quite a restricted interface. So start with the intended milling date in a big endian style. So if we do 240611 underscore the first toolpath in this case, and then you can just check here which tool holder that the tool should be residing in. T1, tool holder 1. And then after this you can add a suffix of your choice. Just make sure not to have any spaces or punctuation or special symbols. So we can do Norrby Skogen, buildings included, and this is the smooth model. And then you can, before clicking post here, you can Control A to select everything and Control C to copy, because that will make it easier when you do the rest, the same thing. Alright, so click post. And here you see that it has been successfully posted. And now we can select the next one and go to actions and post process. And then you can just Control V to paste. And then we change the first toolpath to the second toolpath, toolholder 1 to toolholder 2. And then the suffix can be unchanged. And post. Very good, successfully posted. And then in the third toolpath, we'll do the same. We'll post process and we'll paste. And this is the third toolpath. It's going to be using tool holder 2, the same tool as the previous one. Very good. Post. Successfully posted. And then for the fourth and final, we'll do post process again and Control V. And then we can change this to 4 and tool holder 6. And that is sufficient. And then click post. Very, very good. With all 4 toolpaths verified to be safe to run, with no critical collisions, and with a reasonable expected time to mill. Having all 4 of them post-processed and exported, it is appreciated if you upload these 4 toolpaths to a temporary storage folder. If we go to cnc.kthcnc.se, it's only a URL to a Google Drive, and if you enter the temporary storage folder here, then you can create a new folder. We can call this tutorial, but you can type your name. And then you can enter it, and then you can go to where you exported your 4 toolpaths, and you can just click and drag that here. This makes it really easy to simply download from this folder the toolpaths to the computer that is serving as a server for the CNC. When you have done so, you are finished with the preparations of the digital toolpaths and can focus on preparing your physical stock. Thank you for your time.